Alright, this is the recitation I did last Saturday. In this we go through some more nuances of the nomenclature rules. We do a few IUPAC examples down here. We also discuss the oxidation of carbon and how it produces energy in the body. And we do some IUPAC naming examples down here. We do some IUPAC naming examples down here as well. And for the other part of the recitation, we did part of problem set 2, only the first problem. I should mention right here that where I wrote out this X, that is not the correct orbital energy diagram. I rewrote it over here. I just wrote it out here for this first one to help you get started on that problem. Anyway, here is the recitation, and I will get on YouTube shortly.
Like when you record it and write with it, and then listen to it later on. And if you upload, and if you get YouTube Premium, then you can download this video and carry me in your pocket wherever you go. So the functional groups we've seen all usually contain oxygen or nitrogen or sulfur. So basically, whenever we're looking at functional groups, we're looking at oxidation states of carbon. And some people have asked, well, why is it, what determines the priority of the different functional groups? It's the oxidation state. So the higher the oxidation of carbon, the lower the higher the priority. And looking briefly back at what we did yesterday in our notes, wow, it's way back here. Sometimes I have to delete one note because it takes up like 7 gigs. But, come on, show up. So like we saw yesterday, whatever. Where was it? Right here. So here you saw that going from alkane to alcohol, carbon dioxide going alkane, alcohol, aldehyde / ketone, acid, or you could really say ester too, because it's basically the same. And all the way up to carbon dioxide. Now you see that, well, you understand the oxidation number from that, right? Went over that. So remember that whenever we're talking about oxidation number of carbon, we're always going to be talking about an atom more electronegative than carbon itself. So if we actually look at a chart of electronegativities, I just Googled this, you can find this online pretty easily. Oh, that's pretty blurry. Oh, I can barely read that. I can see it sort of out here. So you see carbon here is 2.5. And then going all the way to the right up to fluorine and down to bromine, you can see that nitrogen, I'll write it in here, 3.0, 3.5, 4.0. Sulfur is about 2.6, I think. Oh, wow. It does straight lines. Sulfur, you see, is 2.6. Chlorine is 3.0. And bromine is 2.8. So all of these atoms right here have an oxidation number, or have an electronegativity higher than that of carbon, which is why you can see that the atoms, specifically oxygen, I don't want the highlighter, oxygen, nitrogen, and sulfur are all in a functional group of their own. When we're talking about contributing to oxidation state of carbon, we're always going to be talking about an atom more electronegative than carbon. But when we're talking about highest priority, we're not necessarily just talking about more electronegative elements. We're talking about the most electronegative elements attached to it. More.
So highest priority.
What I'm just saying is that the more you can see with carboxylic acids and esters, we've got 2 oxygens. Whereas with aldehydes and ketones, you only see 1. So what does that mean? The more electronegative atoms you have attached to a carbon, the higher the priority it will receive.
Most oxidized and more electronegative elements. So you see down here, we have 3 oxygens, 2 oxygens, 1 nitrogen, because 1 nitrogen is a little bit less than oxygen. And then we climb down to oxygen, carbon, nitrogen, and so forth. So now you see the trend, right? So that's really all there is to it as far as the order of the oxidate or the functional groups go. Yes?
You might go back down to that chart. Sure.
Yeah, so I guess for the purposes of this class, nitrogen, oxygen, fluorine, sulfur, chloride, and bromine are all going to cause carbon to be in a oxidized state. Does that make sense?
Which one? Nitrogen?
Nitrogen is N. Carbon, nitrogen, oxygen, fluorine. Yeah, the highlighted ones.
And they cause carbon to be in oxidized.
Yes, because it's a little bit higher, because carbon is electronegativity value of 2.5, but everything else up here is just, even if it's only, sulfur is only 2.6, but that still is enough to pull away electron density away from the carbon atom itself. And just as an important note for functional groups, whenever we're labeling it or determining which atoms belong to which, when determining, like that problem we had where it was like morphine, I think, the atoms in the functional groups cannot overlap. So you see in the carboxylic acid, we have a carbonyl, which is reminiscent of a ketone, and alcohol, which is reminiscent of an alcohol. But when those two groups combine together, we call the whole thing a carboxylic acid. We don't refer to it separately as a ketone, and an alcohol is just one thing. So it's only the carbons in that functional group cannot overlap with something else. Does that make sense? Because really it's about this carbon in the middle. And I'll just go down and circle all these ones in the middle so you know which ones I'm referring to.
So you could call it a carboxylic acid and a ketone would just be carboxylic acid.
Yeah. So these ones I'm circling in purple here are the carbons of relevance. And you might be wondering, well, with these alkyl halides, they're not really a functional group, it's more of an attachment. Or substituent. So this ethers and halides, well, I'll just say alkyl halides. Alkyl halides will almost never go in the suffix of a name. Right. They're basically always going to be as part of the prefix of the molecule you're naming. And with that in mind, now that we understand the functional groups a little bit more in depth, I wanted to pull out a few practice problems for IUPAC and get into more of that. So let me add that picture really quick. What's a good one I had? Here's a good one. Ignore this alkyne one. And also, he said in class, just for now, ignore number 6, because that has to do with stereochemistry, which we have not yet gotten into yet. And before I move further with the nomenclature rules, I should mention that with the increase in oxidation state, increased oxidation state, there is less energy associated with the carbon. Let me move this down so we have room for that. So when we go from alkane all the way up to carboxylic acid, I'll say that's like negative 50 joules of energy, that even though it's more. Whereas if we go from like an aldehyde or a ketone up to a carboxylic acid, say that's like negative 5 joules. Because the alkane started at a lower oxidation state, it has the potential to release more energy. The way in that our bodies generate energy is through oxidation of carbon. Bodies generate energy through oxidation of carbon with oxygen. I mean, we can use it with nitrogen too, but that's really more of a minor species. And so as we're going through these IUPAC examples, let's also find the carbons that are oxidized and label them as alkane, alcohol, aldehyde, ketone. I'll write that on the side over here, or actually you have them in your notes, so that's good. So starting with number B, let's do B together, and then I'll let you choose 1 or 2 to work on your own. That's actually a good one to do. We'll leave that one. So how I like to do it in terms of my own personal rules that makes it easier for me to follow, the first thing I do is identify functional groups. So here in B, we see we've got an alcohol, we've got an alkyl halide, we've got this alkene, and we've got 2 alkyl halides, and of course we've got this alkane chain sitting over here. And the next step, and after identify the functional groups that the carbon is within, then we want to determine can't spell today, highest priority. I'll do this in, what's a fun color? Pink. So what's the highest priority in, oh, I missed the O in there too. So what's the highest priority group out of the ones we've identified so far? Yes, alcohol. What's going to be the next one? Whoops, I don't mean to put a primary there. Alcohol, what's the next one? It's going to be the alkene. And the alkyl halide will be 3rd, and the alkane will be 4th. And just to check that with the list we have up here, alcohol indeed comes first, followed by alkene, 6, 9, and then the alkyl halide, which of course we know will go into the prefix, not the suffix.
Why is it alkyl? How do we know? It's a halide.
Alkyl halide. So the when we change it, you're asking about the eel part. This. So when we go from, so alkane means it's in the chain. When we replace the ane with alkyl, eel, that means it's a substituent. It just hangs off the main chain somewhere.
So it means it's
Yeah.
Did you learn that in class? Just
Not really. But like when you take methane and turn it to methyl, it's not part of the chain anymore. Ethane, ethyl, propane, propyl, butane, butyl. Does that make sense? So if we we made this molecule right here, 1, 2, 3, 4, 5, that's a pentane. And when we have this hanging off of it, that's an ethyl group.
Yeah. Okay. So alkane just means a single bond?
Yeah, alkane is carbon-carbon, carbon-hydrogen single bonds. And alkene is carbon-carbon double bonds. Alkyne, carbon-carbon triple bonds. Good thing we're not getting into alkynes because, well, they create all kinds of trouble.
You said alkane
Alkane has to be carbon, and carbon-hydrogen single bonds. And then alkene is carbon-carbon double bonds. Alkyne, carbon-carbon triple bonds. Honestly, how they come up with like the names and the prefixes and the numbering system for this, I'm not entirely sure. I mean, this one is definitely mostly Latin-based, but not quite, because one in Latin is un, un, not meth. Unless these guys were really on meth. But pentahex, hept, oct, non, dect, those are definitely Latin-based. The first 4, I'm not sure where they come from. So, forgotten that. So after we identify the functional groups, determine their highest priority, now we want to count chain, longest carbon chain. Why carbon? Because it's the most important element in organic chemistry. Count longest carbon chain containing highest priority group. So going here, let's do that in purple. Now let's do it in brown. I really like Notability because I have like a huge palette of colors I can choose from. And I can even make my own, which is really cool. We can make it like this huge red. Let's do that. So the carbon chain is actually easy to identify because there doesn't seem to be any carbon substituents, but we still need to count the total number anyway, because that will turn into our root. So here we've got 1, 2, 3, 4, 5, 6, 7, 8. What does 8 belong to? Oct. And then basically the rest of the problem is simply just telling the reader where does everything else go. Where is it? Why am I here? Where am I going? From a chemist's perspective.
That sounds like
Yes. So we have to tell the reader where the alkene, where the alkyl halide is, and where the alcohol is, or are, because it's plural. So the alcohol is on carbon 1.
So you always start with the highest priority functional group as far as naming the location of them?
Yes. So the root is oct, and then we've got an alcohol, and it's on carbon 1, so we put the 1 before the all. We also have an alkene in there.
If you don't put 1, isn't it just assumed?
Not for, so that's a really good point to make. So with some functional groups, when carbon only has when there's only the one R, it has to be at the end of the chain. It has to be number 1 in the chain. So for these first 4 groups, it's assumed that this carbon in the middle is number 1. Whereas here, where you have like primary, secondary, tertiary, or even just 2 R's, it could be at different carbons within the chain.
That's why you have to label where it starts. But I heard that if you don't put a number, it just means...
For those first 4 groups, yes. For other groups, not so much.
So just from carboxylic acids through aldehydes?
Through carboxylic acids, through aldehydes, the number 1 is assumed. And you don't... It's okay if you still do. It's not a big deal. Where is it? Carbon number 1. And don't forget, we've got the alkene. And so with alkenes, it's kind of tricky because we go from low. We have to, when we say, so it's obviously between carbon 2 and 3, but we just say 2-ene instead of 2,2,3-ene because it's just assumed. So oct-2-ene for that alkene group we see in there. And of course we have 2 chloro groups. So that's just called chloro from chloride. And we see they're both on carbons 2 and 3. So we could say 2,3-chloro, but in order to simplify it just a little bit, we go to the Latin name. Now they're not in meth. So now it's 2,3-dichloro. I don't need the dash right there. 2,3-dichloro. We need 2 O's there. 2,3-dichloro oct-2-ene-1-all. That's how we name that particular compound. And of course, you see we have a double bond in there, which does go off with rule number 6 up here. But again, like, until we get into stereochemistry, don't worry about that too much. Well, worry about it a lot when we get there, but save that worry for someone else. Another time, another place. Isn't that a movie quote? Another time, another place. So, let's do...
Sorry.
Yeah?
So, can you just go over again, like, the order of which one goes in place in the naming group? Like, I understand where the names come from, but I know, like, sometimes it's alphabetical, or, like, that kind of thing.
Right, so let's put this up here in nomenclature. So every single root... Oh, it's even right here, but I'll do my own version so I can annotate it. Or should I? No, it's right here. So the root, you see, contains the longest carbon chain with highest priority functional group. The suffix contains or is the highest priority functional group. And here, since it's an amide, we don't have to label it as 1 because 1 is just assumed. But the prefixes contains everything else. including other functional groups, which is why it's worth mentioning that, that a lot of these contain both suffixes and prefixes. So if the thiol is the highest part of the group, it's thiol. But if it's a substitution, so if we have like a carboxylic acid or an amide somewhere hiding it there, then we label it mercapto.
Depending on where it is.
Yeah.
Okay.
All with hydroxy, bone with oxo, although that doesn't really happen a lot. But once you get into the nomenclature, once you really get a lot of practice with it, it's really not too bad. It's just a matter of learning the language, vocabulary, syntax, grammar of chemistry.
Thank you, that helps a lot. And then it's the other functional groups that you put alphabetically?
Yeah, so when we actually jump up to the prefixes, this is indeed alphabetical. Alphabetical order. Fun fact, alphabet, you might have not noticed this before. When I noticed it was when someone told it to me, I was like, wow, that's really cool. That's actually from alpha, beta, the first two letters of the Greek alphabet. And people think, oh, well, the English alphabet derives from the Greek alphabet, which is true. But the Greek goes back further to ancient Hebrew. Alpha is aleph, and beta is bet, which I believe looks like this. Aleph, bet, alpha, beta, alphabet. So ancient Hebrew precedes Greek. Really cool. And even another cool fact, which I learned in my biblical Hebrew class, is that Elohim, which means God in the Old Testament, begins with Aleph, the first letter of the Hebrew alphabet. So Elohim is the first thing that should come in our lives. And if you notice, well, El is actually the El coming from Elohim actually means like of God. So if you notice, my name actually ends in El, of God. I'll tell you more about my name if you're curious. But seriously, everyone in my family, like all my brothers and siblings, have an El name. Ariel, Gabriel, Daniel, Nathaniel, and Samuel. All meaning of God, something. I don't think so, but it just kind of happened. Like Samuel means God has heard, which is why Elizabeth called her Samuel, because God heard her prayer. You know, wouldn't that be great? You know, like you're sterile for many years, and then it's just like, wow, God, give me a child, and it's like, here you go. Or if you're the Isaac was even more fortunate because, you know, Abraham was worried that he wouldn't get married within the people, within the covenant family, and Isaac didn't even have to go search out for a wife. His servant did it for him. And I think.
See, Genesis 24. The Lord guides Abraham's servant in choosing Rebekah as a wife for Isaac. And let's go down to the story. And here's the servant of Isaac praying, and he said, O Lord God of my master Abraham, I pray thee, send me God good speed this day, and shew kindness unto my master Abraham. And look at this, verse 15, and it came to pass that before he had done speaking, that behold, Rebekah came out, who was born to Bethuel, son of Milcah, the wife of Nahor, Abraham's brother, with her pitcher upon her shoulder. And the damsel was very fair to look upon, virgin, neither had any man known her. And she went down to the well, and filled her pitcher, and came up, See, isn't that really cool? So first of all, Isaac didn't have to go soul searching for an eternal companion. Abraham sent out his servant, and before he finished his prayer, he got an answer as to which person Isaac should marry. Interesting, right?
Because in Genesis 24, where the servant is like, God bless me with a virtuous woman, and boom, there comes Rebecca. So, like, instant gratification. Now, modern days, not so much. Or maybe so, I don't know. God, please give me a wife. Ooh, here she is. Okay. Seriously, it was really quite convenient. And my mother's name is also Rebecca. Very sweet name. So now let's do E together, and then I'll have you work on F, because F is actually a really good one. So C. So again, what are the functional groups we see in there? There's one right here. Alkene. Actually, there's no alkene here. Yes, I thought you said alkene. So yeah, we have an alkane over in this section. We've got a chloro group over here. Chloro. And we've also got an aldehyde. So what's the longest carbon chain? By the way, if it's ever written in the middle like this, that means it's attached. So chlorine is not part of the main chain. So we've got 1, 2, 3, 4, 5, 6, 7 carbons. So what does that make our root name? Hept, yes. Hept. And since we have no other, if we don't have an alkene or an alkyne in there, it's just a straight up heptane. But now we have to look at the different functional groups, chloro versus aldehyde. Which one's the higher priority? Aldehyde, yes. So here, we replace the ane with anal, heptanal. It's very particular about where it is on the chain. Hence, it's very anal.
I'm just concerned that I could definitely figure this out if it was all drawn out.
Yeah, it will all be drawn out.
I can't visualize it super well.
Yeah, it's better to draw. Here, let's draw it out. Whoops.
But do we need to be able to recognize it like this as well?
I don't think so. I googled the problems this morning, and just found these were good problems, so I pulled them out. So you wouldn't have to be able to look at it in this form, more like the stick.
Okay, that I can.
Yeah, I'll just leave it up there. 1, 2, 3, 4, 5, 6, 7. So heptanal, and again, aldehyde always has to be at the end, so it's got to take number 1. It's always number 1, so we don't have to put the 1 in there. The way to remember that is we want to remain anal about it. Whoops. We want to be anal about it, keeping the first position. Then everything else from there is easy. We've got 2 chloro groups, both on carbon 3. So that's just 3, 3, and yes, we do label the number twice if it appears there twice. So then becomes 3, 3, dichloro heptanal, and there's our IUPAC name. Okay.
Why are the 3s there twice?
We have to indicate where the 2 chloros are. So it has to be 3. If it were 1, 4, we'd write 1, 4. We always have to put the number as many times as we need to. So if we had an extra chlorine on there, it would be 3,3,3 trichloride. If we had 4 chlorines, it'd be 3,3,3,3 quadrichloride, whatever 4 is.
And how can we count it that way, like with the chlorines in the middle? Isn't it 2 on the 2 carbon?
Yeah.
Doesn't that interrupt the carbon chain?
Well, if we did this, as it's written in there, it means this. It doesn't mean that it's attached. It means it's attached to carbon, but not in the middle of the chain. So yeah, if it were like that, it would interrupt the chain, and it would be really big. Okay. Part D. Wait, no. Let's do F. F is a really good one for us to work on. So I'll let you. I'll have you work. I'll have you work on that for like, let's say 3 minutes, and then we will work on it together. That is correct. And you see, once you do enough of these examples, it's really quite straightforward. Okay, so now that we've got about, oh, yes, you have a question. So we've got two competing functional groups, right? We've got the ketone, and we've got the alcohol. But the ketone is higher in priority because it's more oxidized. Alcohol lower. So ketone will go into the suffix -one, but even though alcohol is a high priority functional group, it's still lower than that of a ketone. So that's why we put it as a prefix. And so looking back at our chart, in the suffix it would be all, but in the prefix it's hydroxy. Yeah, so a special rule about rings is that the highest priority functional group always is number 1. So 1, 2, 3, 4, 5. And we always want to label the numbers to be as low as possible as well. Hence 2-hydroxy instead of 5-hydroxy. Okay. That was a really, So you can't do these problems. You can do these problems later on your own if you want. I wouldn't do A, but D, E, G, and H would be good to practice on your own. And again, I'll send up these notes as well as make a recording of this video or of this. Yeah, well, my brother's like, oh yeah, you can screen record it while you're like hooked into HDMI. I'm like, ha 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 ha, no I can't. You can see how it's like see how it's just getting mad at me? That's okay though, not a big deal. So I think, oh yes.
Can you like those answers for those next
Yeah, I can put them down here as well. Answers to above. I usually do a pretty good job of. Usually the annotations and notes I make are usually a pretty good set of notes. So I usually just post it as is unless something else is not clear or something. But yeah, I'll post the answers to that if you want. Yes, Natalie?
Can I just take a picture real quick of that?
And the answers to that are right down here. I'm not going to show them, of course, because you can look that up on your own. And now here is me doing the first problem here on this second problem set.
Skimming over this, we've got orbit, boiling point. That has to do with intermolecular forces. Oxidation reduction reactions. Non-covalent interactions. DBEs, double bond equivalents. Draw a circle around each cis, so that's cis and trans, which we haven't gotten into yet. Rank the following molecules in amount of unsaturation, so that's DBE again. So the problems you should be able to do right now are 1 through 2, wait. you should be able to do 1, 2, part of 3, and 5, based on everything we've covered up to this point. For the oxidation reduction reactions, make sure you go back to look at the table of going from alkane to carboxylic acid. And then you should be able to do that problem just fine. So, yeah. So is there one of those problems you would like to work on here? Yes?
I did all of one, except I wasn't sure how to draw, because this is what I'm thinking. For the second part, like, is the order right? And then also, how would you draw the shapes, like the pi bond, on top of the whole molecule?
How do you draw it on top of the molecule itself?
Yeah, like the constructive and deconstructive pi bonds.
Oh, so the deconstructive and the constructive you would actually draw on the molecule. So those are two separate orbitals. Deconstructive, constructive. You only write the one that's participating in the bond.
Well, you have to draw the homo and the mole, which are both participating.
Right. So, but you don't. What I'm saying is you don't draw them both at the same time.
Right.
So.
I still don't know how to draw them separately, though.
Yeah. Let me do that for you. I'll do. Which one do you want? Do you have a preference? I'll just do the first one.
Sure.
Okay. Homo and LUMO. Consider the following molecules, indicate which are the frontier molecular orbitals, HOMO and LUMO. Remember, HOMO is highest occupied, LUMO is lowest occupied. Even though H comes before L, it's always L on top of H. You go from low to high, not from high to low. Indicate which are the frontier molecular orbitals. Redraw each molecule twice. On one of your drawings, draw the HOMO, and on the other, draw the LUMO. So let's just draw the what is it called? The overall orbital diagram, I guess. So for this, it's going to be, we've got carbon, carbon, sigma on the bottom, full of 2 electrons. Let me draw them all first. Then we've got carbon, hydrogen, sigma, and we've got 4 of those. We've got carbon, carbon, pi. Let me move this down so I have enough room. There's 1 there, and then, of course, it just all climbs up into pi star, carbon, carbon, sigma star, and 2 carbon, carbon, sigma star. 1, 1, 2, 3, 4, and 1. So filling up the orbitals, we go 1, 2 for carbon, carbon, sigma, then for carbon, hydrogen, 1, 2, 3, 4, 5, 6, 7, 8, and then 2 in the pi. So that's the total orbital energy diagram for for ethylene itself. And then identifying the HOMO, I will do that in purple. Purple is the color of royalty. HOMO, highest occupied, is just this one right here. And the LUMO is just the one right up to it. So the two orbitals we have to draw are the HOMO and, well, the pi, HOMO, and the pi star LUMO. So remember that the pi comes from 2 separate p orbitals. So the initial state of that was we took a p and a p, not literally, and we created the 2 opposite states, one with the constructive interference and one with the deconstructive interference, leading to pi and pi star respectively. So the constructive interference, the in phases overlap with each other. So what that looks like completely is this. And like 2 little, looks like a, what does that look? It looks like a sandwich. or maybe a surprised Arabian man. Do you see this? Here's the turban right there. And then shading on the top. Okay, now he's Arabic. And then the deconstructive will just lead them out of phase. Now I should draw on the top to be more consistent. Now we're going to top. Now we're going out of phase, and then we have a node down the middle here. So we saw earlier that the pi in pi star was the HOMO, and this was the LUMO. And I'm quickly running out of space on this sheet. So I'm going to draw it way down here. So to draw the LUMO, let's do the HOMO first. Unfortunate name. So to draw the HOMO, we literally just draw it right on top of the molecule. So we don't need to include the two little circles because those are the carbons. So what we do is just go one above right here, and one below right there. It's still Arabic. Now he's just looking. Now he's just looking that way. So that's how you draw the HOMO. Maybe a little bit neater because that's not super great. But then drawing the LUMO.
The two things are the carbon residues.
Yeah, the two little dots.
That are flanky. Okay.
Yeah. And then the LUMO. Honestly, I'm surprised that this is on this week's problem set and not last week's problem set. But that's okay, because now we understand more. So the LUMO, again, drawing the molecule. Becomes that. And what does that look like? Let's switch back to purple. We've just got two p orbitals. Well, I should draw it as part. It's the carbon at the middle. I just don't want to draw it at the middle because then it blocks up the picture. So then we have the two p orbitals just like that. Out of phase like that. They don't overlap to make the surprise Arabic man looking to the left. And there you go. That's how you draw it.
So we don't have to draw the
Not in the atom itself. Looking at it, it's already implied.
Alright, so that is the first part of problem 1. As you see here, I start out the electron configurations for you, starting with the sigmas and then the non-bonding electrons on the oxygen right there. Keep in mind that this is not the full thing. You still have to do that. You still need to do the anti-bonding because the non-bonding is gonna be your HOMO, and the next one up is going to be your LUMO. HOMO, LUMO. And then again, I just wrote this out to help you get started. Hope you can succeed on this homework assignment. And that is a review for today.